Welcome to the Earth Science Classroom. Welcome back to the channel that basically covers all of Earth science topics, geoscience topics, physical geography topics for ages pretty much from 11 to 18 and beyond into college and university. So this video is on tides. It's the part 3, follows along from obviously part 1 and part 2. And in this video, we're looking at what is dynamic theory. All right, so to do with tides, and what are the variables introduced with dynamic theory, okay, as well, different things that go along with that, and looking at tidal features, things like the tidal flats, tidal deltas, tidal current, okay, as well, and then we'll look at the end, beaches can be classified into either tide-dominated coastlines or beaches, and wave-dominated beaches or coastlines. All right, so join me now. All right, so what is dynamic theory? Now, this is an advanced theory. Advanced theory, which goes or basically adds on to the equilibrium theory. Now, this was discussed by Isaac Newton when he was developing his principle of gravity and forces, the 3 laws of gravity on Earth and the 4th law in astronomy, with 2 masses, mass 1 and mass 2, and looking at the gravitational pull of each of these celestial bodies, say planets or stars, and also looking at the distance between them and figuring out the force of gravity and where the point is where those 2 forces meet. Obviously, the larger the mass, the more gravity. So there's interactions between these bodies. Now, based on this, Newton in 1687 looked at basically tides and the force applied on Earth by gravity, and gravity of mostly the moon and partly the sun, and the effect it has on the oceans of the Earth, which is tides. And in the other part 2 and part 1, we discuss what tides are and tidal range, and look at the interactions between the moon, sun, and the Earth to create the tidal cycle and patterns. And Newton stated that if just in terms of astronomical factors, just considering the 2 objects in play for gravity, the distance between them, and the fact that, let's say, the planet is just a whole big ocean. There's one big ocean. There's no land masses. It's just ocean. He theorized that there would be a semi-diurnal tidal pattern, and that it will be the same all around the Earth, because the Earth is just one big ball of sphere of water, and it's just controlled by gravitational forces or astronomical factors. So that was the theory, equilibrium theory. Everything is equalized based on gravity, and the tides would react to the forces applied. Now, we know that the planet Earth is pretty much one big ocean, about 70% ocean. But if you don't consider the 30% of land, then you're not going to get an accurate estimation of how tides work. Also, the oceans are vary in depths and various features on the ocean floor and seabed that would affect it and cause frictional forces and various other variables. And that leads us back to our original question: what is dynamic theory? So it's basically you take into account around 400 different variables, which would affect the tides and in addition to gravity. So this is in addition to the forces of gravity, the big G right there. Now, these 400 variables can come in small sizes or small fluctuations to large fluctuations. And they basically create different tidal patterns we discussed in part 2. Now, there are cyclic patterns, which is between the sun, the earth, and the moon. Let's say spring tides and neap tides, okay? When the moon's in a certain position around the earth and the sun. So those are cyclic and those are pretty much consistent. However, tidal patterns are down to the variables around each location or coastline, which could change the patterns. So you might have a mixed pattern where the high tide is different levels or ranges. You have a semi-diurnal, which again, diurnal means day, so 2 high and 2 low per day. Just a regular diurnal is 1 low and 1 high per day. Again, these are discussed in part 2. But these variables, this dynamic theory, accounts for why there are different tidal patterns around the planet. Because, as you can see by these lovely pictures on the right-hand side, there's land masses and a continental shelf and continental rise and slope that's going to change and adapt how these shallow tidal waves really work and oscillate around the planet. Now, if you have a, if you have a tank of water, okay, you have a tank of water, and you are going to move it, let's say, and have the effect of a tide. So let's say the moon is over here, okay, and of course the water is going to be dragged towards the moon, right? And as the moon is going to revolve around your tank, let's say your given ocean area, that water is going to respond and move and reflect off and rebound off the sides. Now these sides, this could be an ocean basin, could be the Pacific, could be the Atlantic, or it could be a small bay or an inlet. But it's going to move back and forth according to where the moon is and the sun. Now, these other variables are going to the shape of the coastline, the depth, and are going to affect, as I said, again, these 400 variables. But it's going to oscillate and move, and when it refracts and reflects off the sides or the coastlines, it's going to create what's called a stand-in wave. Now, in reality, what happens is the water is going to start moving this way and this way. I'll just turn different colors. This way and this way. So go up and down. So there's a point in which the water, say right here, so the red circle, point here indicates where the water is going to oscillate and rotate and move around, like a central pivot. Like a central pivot. Like a seesaw, right? So like a seesaw in a kid's playground. You know, one side goes up, one side goes down. Here's my seesaw. One side goes up, one side goes down. But this pivot is kind of staying in the same place. It's not really moving. There's no real vertical change. And this central point in terms of tides is called a nodal point, or sometimes called a anthrodromic point. Now, this is where the water is going to, ocean water caused by the tides is going to oscillate around, and it's kind of a static point in the sea level as the either side. So here, the tidal range is basically zero. The effective tides is basically zero, right? There's zero range. Whereas further away you are from the nodal point or amphidronic point, so you're on the edges, so you're on the coastlines, where the ocean's going to interact with the land, you have the largest range. So in theory, the further away you are from that nodal point, the larger the range is going to be, again, according to different variables. So if there's a nodal point in let's say the Atlantic that's close to a certain coastline, then that coastline is going to experience a smaller tidal range. For example, the east coast of America, New Jersey, Delaware, Virginia, North South Carolina, Florida, experiences a smaller range generally than the west coast of Europe and England and France and Portugal because it's further away from the nodal point in that Pacific Ocean, the Atlantic. So where that nodal point is very important, and there are multiple nodal points all around the world in different locations in each of the oceans, and that corresponds to how the oscillating ocean water behaves in each ocean basin, and will control a lot of the tidal ranges of the coastlines. And that will also control the tidal range, the amount of erosion and deposition and transportation of sediment and coastal processes. All right, so now on to the variables. Now, I mentioned a few variables earlier, and this is all based on the dynamic theory. So obviously the nodal point and where it's located in each ocean, okay, is going to affect a lot of the variables for the coastline tidal range. Also, the moon's oscillation, the moon's movement. Besides the obvious, here's the Earth and here's the moon, besides the obvious 29.5-day half-day revolution, okay, it's also going to fluctuate between 20. So here's the equator. It's going to fluctuate between 28.5 degrees north and 28.5 degrees south. So that range of where the moon is in respect to different latitudes around the Earth is going to affect the tidal range as well and the strength of the tides. Also, your latitude on Earth. Obviously, the equator is at 0 degrees and the North Pole is at 90 degrees north and the South Pole is at 90 degrees south. So your latitude and how far you are away from the equator or the poles is going to affect. Now, obviously, 28 degrees just above the Tropic of Cancer and just below Tropic of Capricorn. Obviously, if you are in, let's say, 60 degrees north, okay, or let's say you're at 0 degrees on the equator, like in Ecuador, then you're going to have a different tidal effect because of the latitude and the strength and how close you are in terms of the moon and also the shape of the Earth being a sphere, and the shape is going to affect also the amount of tidal range you get at certain latitudes. Then you have the coastal seabed morphology. Okay, the depth, the gradient, the slope, features. Is it gentle slope? Is it steep slope? That is also going to affect the tides as well. Also, is it an open coast, or is there going to be a lot of bays and inlets and areas where the tides can be pushed up and the tides can be interfered with, and they can basically overload each other and build up build up the waves by refraction and reflection and cause a larger tidal range, which also is what causes tidal bores. And the last main one is the Coriolis effect. Okay, the effect of the spin of the Earth and the shape of the Earth being a sphere, and it's the deflection of air and water going away from the equator, because the equator is moving faster than the higher latitudes going towards the North and South Pole. So when, let's say, a hurricane, or let's say an ocean current, whatever, is going from the equator north, in the northern hemisphere, is going to deflect to the right, and in the southern hemisphere, it will be deflected to the left. So again, these major variables can affect the tidal range and tidal behavior. All right, so as we look at tides, we're going to look at the features. What are the features that are associated with these tides? And the first one that comes up is called the tidal current. These are the longest waves, the longest period, and wavelength. Because they're so long and wide and long time, that they act as shallow waves, which is weird, because they're usually an open ocean, which is very deep. But there are certain characteristics that need to happen to be a long wave versus a shallow wave. So because they're so long periods, long wavelengths, they are classified as a shallow wave. So because the wave propagates a certain way, all right, so let's draw a wave right there. There's movement. Basically, there's very little vertical movement. There's very little vertical movement. So no vertical movement, or very, very small. The majority of the movement happens here, where there is horizontal movement of water, and this creates a nice consistent current. And it's going to flow through as it oscillates around the nodal point, as discussed, in each ocean basin. And we can see it. And the current is divided into 3 parts. Okay, so when the current is pushing the water towards land, so let's just do the land right here. Here's the land, here's my beach, and here's my ocean. Okay, when the tide is coming in and going up the beach, we call this a flood current going towards the beach. And then when it goes away and comes back and retracts and goes up. Now this is different to swash and backwash with waves, because this is not really a wave in a wind wave. This is a tidal wave, a tidal current. And going back away from the beach, it's called an ebb current. Now there's a point in which there's no movement between flood or ebb. When there's no movement, we call this slack water. So it's in between the time in between ebb and flood. So slack water is where there's kind of like a stationary pause in between the two types of movement, either flood or ebb. So what do we care about tidal currents? Obviously, they're consistent, they're worldwide, and they can basically cause erosion in a small amount. They can cause transportation and allow for a load and sediment to be moved by the currents, by the ocean water. And obviously, they can, when it loses energy, it can also incur deposition of such bed load, of such sediment, and cause geomorphological features around the coastline. Okay, some of those features. So let's say you have a tidal inlet. Okay, let's just say you have, let's say, take this diagram up here. Here's my inlet. Okay, here's the coastline, and there's a little headland right there. Okay, and there's a little inlet right here. So the tide is going to be concentrated and increase through this inlet, and it's going to open up into a larger bay. Now, the speed is going to be fast with more energy right here through the inlet, through the passage, like through the doorway. Once the tide goes through, it's going to hit a larger area and it's going to slow down. And that's going to cause any sediment to be deposited in this area right here. And what you could do is it could basically incur an accumulation of sediment to cause what's called a tidal delta. This is the same as a river delta, where it fans out and drops all its deposit. But same thing, but the opposite direction is going towards the coastline from an inlet into a bay or a lagoon or a sound or an estuary. So tidal delta, so in goes the tide, and here's the, I'm going to draw the land right here. Here's the land. Here's my land. Okay, so here's the ocean. Here's the tide coming in. Here's the flood current coming in, and here's my lagoon. Okay, and there's another bit of coastline right here. Okay, here's my lagoon. So it's going to fan out the tide, and it's going to deposit and cause little bits of deposit right here and cause a tidal delta. Now, in between, in the intertidal zones, you might actually get a larger amount of sediment on the sides right here, because maybe the main part of the current goes straight through the middle right here, but on the sides, when it's low tide or there's an ebb current moving out away from the land, these sides could be exposed to longer periods of basically no water, so they can deposit, and what you have is you can start to create what's called tidal flats. Could have mud flats, or you could have salt marshes. Now, salt marsh depicts there's more vegetation going there, more vegetation that can grow and survive in very salty water with consistent water and a high water table, brine environments or brackish environments where you get those mangrove forests. You get certain weeds and certain vegetation that grow in these salty water conditions, but they're tidal. They're controlled by the tide. So during high tide, they'll be underwater. Low tide, they're exposed to the atmosphere, and they're basically out of the water. So these are amazing features that are caused by the tidal currents and by the certain coastal landscape and geography. So you have some cool pictures here, images of various salt marshes over here, the far left, and here in the middle, you've got a very nice exposure of some deposited material. And for low tide, you can see the boats here on the right-hand side with the high and low tide. And at the bottom right, you've got this subtropical, tropical environment where you've got this tidal inlet coming through here. And you have the kind of like these floodplain type areas on the sides of the water where during high tide, obviously, you can see that the water's going to come up to around here and cover these vegetation and mangrove trees right there. And it's dictated by tides, and the whole ecosystem, the whole morphology and the shape of the land is dictated by the tides in these areas based on the tidal range. All right, so final thought on tides and tidal features is that you can classify a coastline or a beach by whether it is tidal dominated or wave dominated. So wave dominated would be like in the bottom right hand corner here, where you've got lots of wave action, hydraulic action, abrasion, and maybe like a prevailing wind, large fetch, but you've got lots of waves, breakers, surf zones, which really control all of the coastal processes. Now, generally, there is a low to small tidal range with a wave-dominated coastline, and you'd have minimal range, so there'd be a small intertidal zone. So the waves are pretty much dominating the processes and erosion, whether it's a productive accretion example or more of a destructive situation where the waves are breaking the coastline and different processes, different landforms are being created. Compared to a tidal or tide-dominated coastline, we have over here where we see large tidal range. We have limited wave action. Okay, and most of the processes, most of the landforms are created or allowed to be created because of the tides and tidal ranges. So you get more salt marshes, you get also very simplistic coastline rather than more of a jagged, more harsh, wave eroded hydraulic action coastline. All right, guys, thanks for the watching the video, and I'll see you soon in the next video. Thanks.